Okay, everyone. So today we're going to talk about titration in general. I think most of you have already done titration experiment in GenChem, right? The basic acid and base titration. For titration, you have analyte in LML flask. Most of the time, you will have an indicator to indicate the color change at the endpoint. And with the burette, it's filled with titrant. So for example, your analyte can be acid and your titrant could be base. And the indicator in the LML flask will tell you when the titration is done, right? Okay. So the titrant is defined, is put into the burette, and it's added to an unknown solution of analyte until the analyte is exactly consumed by the reaction. And we also call this process as volumetric analysis. So still remember last time we talked about gravimetric analysis. In gravimetric analysis, we use the mass of the product to determine the amount of analyte in the original compound or original sample, right? Versus in this case, the quantity of analyte present is calculated from moles or millimoles of titrant consumed or required based on the stoichiometric ratio. And how do you know the moles or millimoles of titrant consumed or required? We use burette, and by using burette, you can tell like how much volume of titrant is being used. And as long as the titrant has a known value or it's standardized. So here we talk about standardized. Standardized means that you're using another primary standard to tell the concentration of the titrant. But anyway, as long as you know the concentration of the titrant, by using the burette, you can tell like how much volume of the titrant is needed for consuming all the analyte in the solution. And then based on the stoichiometric ratio, you can calculate the quantity of analyte present, right? So here the stoichiometric ratio is very important. It's not always 1-to-1 ratio. For example, this is going to be your force lab. In the force lab, you're going to titrate sodium carbonate with hydrochloric acid. And you can see here from this reaction, it is 2 hydrochloric acid needed for 1 mole of sodium carbonate, right? So for example, if based on the volume of the titrant and the concentration of the titrant, we determine that, for example, 1 mole of hydrochloric acid is used to titrate the sodium carbonate, then how many moles of sodium carbonate is present in our original sample? This is a question for you guys. If I used 1 mole of HCl, how many moles of sodium carbonate is present in the solution? Yeah, it's 0.5, right? Because it's 1 mole HCl and multiplied by, for every 2 mole of HCl, it reacts with 1 mole of sodium carbonate. So it's 0.5 mole. Okay, all right. Moving forward. And we have 2 different terms here. The first one is called equivalence point, and the second one is endpoint. Anybody knows the difference between those 2? One is experimental, the other is theoretical. That's right. So which one is theoretical and which one is experimental? That's right. Equivalence point is the theoretical point, and the endpoint is experimental point, for example, determined by an indicator, right? Right. So equivalence point is theoretically when the quantity of added titrant is the exact amount necessary for a stoichiometric reaction with the analyte. So this is the theoretical finishing point. Well, the endpoint is something we use to determine or show the equivalence point, which is marked by a certain change in a physical property of the solution. So a very common example is the color change, right? So when you use an indicator as an endpoint, the color will change. So you know that we have to stop the titration and we will use that volume to do the calculation. Now, in reality, the endpoint might not be exactly the same with the equivalence point. For example, for acid-base titration, maybe the equivalence point, you're looking at a pH of 7, right? But the indicator you use, it might only change color when the pH reaches 7.2, because the indicator, the change color is also related to the equilibrium associated with the indicator itself. And it has its required pH to change the color. Now, we say that from 7 and 7.2, there is a 0.2 difference, right? And the difference between the endpoint and the equivalence point is called a titration error. Now, my question for you guys is, this type of error, is it a systematic error or it's a random error?
A random error?
Why do you think it's a random error?
Because it's based on the measurements and also how accurate the indicator is.
Mm-hmm. Any other opinions? Okay, so I want to clarify on my question. The question can be asked in two different situations, okay? Number one is when you're doing the experiment, you need to visually decide when the endpoint is, right? Because the color is changing, so you have to decide when the color reaches the color you want. So for example, if it's from colorless to pink color, so you have to decide where the color is. And when different people are looking at the color, so there might be a slight difference in where the endpoint is. If we're talking about this situation, is it a systematic error or it's a random error? I'm asking about the error associated with visually deciding where the endpoint is.
Random error?
Should be a random error.
Yeah. So this case, it's definitely a random error, right? Because you have to make a decision whether the color is the pink color, or in reality, actually in the pH experiment, the sodium carbonate experiment, you're looking for a color change from pink to colorless, but it is very tricky. It doesn't change to pink, it doesn't change to colorless completely. You still see some little pink shade there. So you have to take some decision here, whether I have to stop now or whether I have to do a little bit more. So that there is a random error associated with that, right? But the question I was asking before this is, I'll repeat my question. So for example, when you do a strong acid, strong base titration, you know that at the equivalence point, all the acid or base are being consumed completely. So you should have a neutralized solution, and the equivalence point should have a pH definitely at 7.0, right? But the pH indicator, the titration indicator you use, it's normally a weak acid or a weak base, okay? And the pH at which they change color is associated with their Ka or Kb, all right? So for example, in this case, the indicator we use, it changed color at 7.2, okay? It always change color at 7.2. Now, the 7.2 versus the 7.0, there is a 0.2 difference. Do you think this is a systematic error or a random error? Think about the question again. Yes, the random error I mentioned in the previous question comes from the uncertainty of telling whether the color is really pink or really clear. And also this, for example, for the sodium carbonate titration has 2 steps. The first step is pink to colorless, and the second step is colorless to pink again. But that pink color is also a little orange. So there's uncertainty of telling the shade of the color. So that's a random error. But the other question I'm asking is, when you're using an indicator that changes color at a higher pH than your equivalence point, is that a systematic error or a random error?
It'd be systematic, right?
Systematic because it has to do with the strip itself.
Yeah.
Yes, that's right. So that part is a systematic error. And if you think about the titration process in general, it actually contains both the systematic error and the random error. So the random error comes from the uncertainty of telling the color change, and the systematic error comes from the systematic difference between the endpoint and the equivalence point. The endpoint is determined by the indicator you use. And when you use a certain type of indicator, it will always change color either above the pH or lower than the pH, depends on what indicator you use. But if you're using a specific indicator, it will always be positive or always be negative. Okay, so there isn't a random uncertainty associated with that. Okay. All right. And